Good afternoon, dear participants of the fifth International Profit Conference. Let me introduce myself. My name is Yuri Skob. I am a presenting author of the report on the topic Mathematical Modeling of Hydrogen Deflagration in Enclosed Space on behalf of a team of authors from Ukraine. The study aims to analyze hydrogen gas concentration and pressure fields in an enclosed space following an accidental hydrogen release, explosion, and subsequent shock wave propagation using mathematical modeling. The research focuses on the physical processes of gas-air mixture formation and explosion dynamics in typical garage conditions. A mathematical model describing gas movement and chemical interaction during deflagration and shock wave development was developed. The modeling employed an explicit time-dependent finite difference Godunov method of first-order accuracy. The relevance of the study is determined by the need of the community of experts in the field of safety assessment of high-risk industrial enterprises and such civil objects as garages for reliable and effective mathematical models that will allow simulating complex physical processes that arise during an accidental release of such explosive gases as hydrogen into the atmosphere. Such models should replace expensive large-scale physical experiments for analyzing and predicting the consequences of an accidental explosion for the environment. The instant release of a given amount of gaseous hydrogen is considered. The admixture forms a gas-air cloud which moves under the influence of the wind. The system of differential equations of motion of a three-component gas mixture includes the laws of conservation of mass, momentum, and energy of the mixture, supplemented by the laws of conservation of hydrogen and combustion products mass. The equation of state of the mixture completes the system of equations. According to the suggested combustion model, it is assumed that the chemical reaction takes place in the elementary volume with a rate that can be determined under consideration of the chemical brute reaction. The molar change rate is determined using the parameters obtained on the basis of experimental data generalization and Arrhenius reaction constant. The density change rate of the combustion products is determined on the basis of the law of mass motion. The developed mathematical model of gas deflagration was validated using data from physical experiments and other model simulation results. Firstly, an explosion of the hemispheric homogeneous stoichiometric hydrogen-air mixture cloud was modeled experiments at Fraunhofer ICT laboratory under the ambient conditions. Secondly, the pressure development at distances of 35 meters, point B on the figure, and 80 meters, the point D, from the epicenter of the explosion at the point A, was examined during the computation. Validation of overpressure in the blast wave front was carried out by evaluating the recommended statistical indicators. The overall quantitative and qualitative analysis of the compression phase of the blast wave at the control points, taking into account the parameters of the wave's impact on the environment, gives acceptable results. The model overpressure history in control points B and D is shown in figures A and B and compared with the large-scale physical experiment and the results of other models. The computational results show acceptable accuracy and allow us to consider the developed mathematical model as an adequate instrument to simulate gas explosions. Using the developed mathematical model, the deflagration explosion in the standard civil garage premises was simulated. Two potential scenarios of hydrogen concentration were considered: stoichiometric and large concentrations. It is assumed that the hydrogen is released due to the destruction of the fueling vessels stored in the garage space. The doors, windows, and gateways of the garage building during the deflagration are open. The hydrogen and combustion products mass concentration field, overpressure, and temperature history were analyzed. The same parameters were controlled during the second scenario simulation. All diagrams testify to the more intensive development of such harmful factors as the maximum overpressure and the momentum of the compression phase of the shock wave. And finally, the following conclusions can be formulated as follows. A validated mathematical model was developed to simulate gas mixture deflagration and the dispersion of combustion products in enclosed spaces. The model's accuracy was confirmed through comparison with experimental and numerical data on hydrogen deflagration. Numerical simulations provided time-dependent fields of pressure and concentration for different hydrogen cloud scenarios in standard garage conditions. The resulting distributions of overpressure and impulse were analyzed to assess potential shock wave impacts on nearby structures and people. The obtained results can serve as a foundation for safety assessments and AI-based classification of hazardous zones in hydrogen-related industrial facilities. Thank you very much for your attention.